All right, thank you, Joel, and thank you to everyone for being here. Thank you to the advisors for inviting me, or organizers, I'm sorry. This is, I believe, my 7th year here, which is getting kind of hard to believe at this point, but it's always great to come. So I was going to tell you guys about some fire simulations focused on local group pairs, so basically an extension of the Elvis work that I've talked about here in the past. Fortunately, those simulations, due to a lack of CPU time, are not quite ready. So we're holding off on that till next year. In the meantime, we can talk about faking it until you make it. So what do I mean by that? Well, hydro sims are fantastic, right? We've been hearing all week about how great hydro sims are. They include all these excellent things like supernova feedback and galaxy formation, which is what everyone here wants to study, right? They include AGN feedback. And importantly, they include the interactions between the baryons and the dark matter. So for example, this is just showing what happens to subhalos around the disk. And this is showing, this is from Jose Añurbe, showing the effect of a density profile in isolated dwarf under supernova feedback. Now, these are awesome. They can compare directly to data. And not only that, but because they include more physics, I think we can pretty reliably say that they are at least more correct than dark matter-only simulations. So what do I mean by that? This is a plot from the latte simulation that I thought Andrew Wetzel was going to be presenting here earlier, but he couldn't make it. I don't really want to talk about too much of the physics involved in latte. What I mostly want to talk about is the difference here between the dark matter-only run plotted in this dashed line and the full fire simulation. So this is plotting the number of subhalos as a function of mass within 100 kiloparsecs of the center of the halo, a redshift 0. I'm counting only the dark matter, but I've also reduced the particle masses in the dark matter only run by 1 minus the baryon fraction. So what you can see here is that we overpredict in the dark matter only run by a factor of about 1.5 to 2, particularly within the central 100 kiloparsecs, right? This is not particularly new. People have seen this before. We also see huge differences in the radial distribution of subhalos. So this is plotting number of subhalos within some radius. I'm making a cut here at 3 times 10 to the 6 solar masses, which is basically a resolution limit for latte. And you can see that we overpredict by a factor of 6 to, well, infinity here, within the central sort of 20 to 50 kiloparsecs. This is a big deal, right? Now, so these are great. The problem is they're really, really expensive, right? How expensive is this hydro simulation? Well, latte took 1.1 million hours, which is actually pretty quick for the resolution that it runs at. The dark matter only version of latte took just over 6,000 hours, CPU hours. That's a factor of 175, which means that in principle, you could have simulated 175 halos in dark matter only in the same amount of CPU time. And like I said at the beginning of this talk, CPU time is not free, right? So that means that you can't really do statistical samples of baryonic simulations, at least not yet. So is there a third option? And I'll note that I stole this talk, or this chart, I apologize, brazenly from your talk last year, Andrew. It was a great idea. The third option turns out to be what I call embedded potentials. So what do I mean by embedded potentials? Well, here is a dark matter halo, right? It has some density profile. It's got a bunch of subhalos flying around within it. But what's missing from this picture? The galaxy at the middle of the halo, right? This is what we want to study, but this also is important for the substructure. Now, unfortunately, this thing is in a cosmological simulation, so it has some really complicated trajectory where it's flying through space. So if we want to model this, what I'm going to do instead is stick basically a massive sink particle. You can think of it kind of like a bulge. And through dynamical friction, that massive particle basically tracks the halo center. And we've tested this, and it works quite well. At redshift 0, our sink particles are all well within a softening length of the halo center. And then we're going to attach a disk to that sink particle, basically. And at every time step, we just add an extra acceleration to every dark matter particle. And we are then going to scale this disk to match the galaxy that forms naturally in the fire simulations. Now, is it cheap? Can we do statistical samples of this? Well, it's about a factor of 2 more than the dark matter only simulations. which is basically just coming from the fact that you've increased accelerations at the center of the halo. But that's not really a big deal. I would argue that we can still do statistical samples. 75 halos is a statistical sample. Is it right? Well, we're not going to get supernova. We're not going to get AGN. We're not forming stars, really, but we're kind of forming a galaxy. We're definitely not going to get this, but that's okay. But we're really going to capture this effect very, very well, right? That's what we're going after. So I think that's an open question, but let me just throw up 3 visualizations here. These are the latte simulation again. This one, I'll give you this one. This one's dark matter only. Now I want you guys to guess which one of these 2 is the embedded disk and which one of these is the full hydrosim. Anyone who thinks A is the hydrosim? All right, that's about, you guys are good. So B is the hydrosim. The best way to tell, you may have guessed, is the fact that this actually forms a little bit of a dark disk in the center. That's really just coming from the fact that we're holding a disk fixed in orientation. So it has about 9 gigayears or so for all the dark matter to just coalesce onto it. So let's quantify these changes, right? You can see immediately that there's a huge difference in the substructure populations between our embedded disk run and our dark matter only run. So one, we can ask how much of the stripping and destruction is due strictly to the central galaxy, because that's the only extra physics that we've added in, right? 2, we can ask how well do we reproduce fire with the potential? In other words, is this a viable alternative to running full hydro simulations in order to get statistical samples? And I'm going to convince you, hopefully, that the answer is yes. So here's that same mass function again. This is, like I said, latte. Dark matter only and fire. If I put the disk simulation on there as a dotted line, you can see that we have reduced the amount that we over-predict the substructure from about 1.75 to about 25% at worst, right? We have a second halo that has not yet been published, but it has identical physics to the latte simulation, identical resolution. Like I said, I had hoped Andrew was going to talk about it. You can see that we're doing even better in this halo 2, actually. I can talk about why I think that's happening afterwards if you guys are interested. The point here that I want to make, though, is that only including the disk brings the dark matter only simulations into agreement at about the 25% level. That means that the central galaxy is responsible for 2/3 to 75% of the substructure stripping and destruction within the central 100 kiloparsecs. So the central galaxy is hugely important. We can also look at radial distributions. So again, here I'm plotting halo 1. This is latte again. Same line styles and everything. And if I add the disk on, you can see that again, okay, it's not perfect. We have 3 subhalos within this sort of 20 kiloparsecs that don't exist in the fire run. That's 3 subhalos. It's not actually terribly awful. And we're, again, within about a factor of 1.5 to 2 at all radii. If we look at our second halo, we're doing even better again. And like I said, I can talk about why I think that is afterwards. But again, I want to make the point that at the small radii, we're over-predicting by a factor of at least 5 to 10. And that we can see that very clearly the disk alone is responsible for about 75% of that destruction at the small radii in particular. Now, is this important? The answer is yes, very important. People have been looking for these tiny subhalos through, for example, gaps in cold stellar streams coming from globular clusters. I have highlighted here where GD1 and Palomar 5 live around the Milky Way. You can see that while dark matter only simulations predict that you should be seeing of order 10 things flying through these streams today, if you add in a central galaxy, that number drops to about 0, 1 to 0. Now, that's not the full story, right? We know that these streams may have been caused by subhalos that are now gone, but I'll get to that in just a moment, actually. So, takeaway point, just adding the central galaxy lets us match the mass functions and the radial profiles at about the 25% level compared to of order 100 to 500% errors in dark matter only. So, the next question I want to ask is which subhalos are destroyed, because that's really most of what we're seeing here. So what I'm plotting here is a mass function as a function of peak subhalo mass, so the largest mass that the subhalo ever attains. And straight away you can see that there's just really no strong trend in M-peak. The galaxy is destroying substructures at all masses, right? So I'll ask the question again, let me also make the point though that the disk is always a better match to fire than the dark matter only simulation. And this is actually true both in everything I've shown you so far and everything I can show you in the future if you're interested. So I'll ask the question again, which subhalos are destroyed? Because that didn't answer the question. You might think, well, it's subhalos that get close into the galaxy, and it turns out that is exactly what's happening. So here I'm plotting the distribution of paracentric distances normalized to the total number of subhalos. The bottom panel, though, does not include that normalization. I'll get to that in a moment. But you can see that our median paracentric distance in dark matter-only simulations are around 20 to 30 kiloparsecs. These are paracentric distances of objects that remain within 100 kiloparsecs today, whereas when you add in the central galaxy, that goes up by about a factor of 2. Goes up to about 40 to 60 kiloparsecs. You can also see, this is, again, the bottom panel is plotting the ratio and the absolute distributions, that you would overpredict the number of subhalos that have passed through Palomar 5 or GD1 by about an order of magnitude. So that's a huge, huge deal, right? That means that you should see something in the tangential velocity distributions as well, right? Or radial velocity, if you want to look at it that way. Subhalos that are on radial orbits that bring them close to the center of the galaxy are preferentially destroyed in our fire and disk simulations, right? And again, the disk run is reproducing the fire simulations very well and capturing this destruction that just doesn't exist in dark matter only. One last thing that I put together earlier today. This is extremely preliminary, but I just tossed on the tangential velocities of Milky Way satellites within 100 kiloparsecs for the ones that we know. This is only, I think, about 7 or 8 of them, but hey, it's something. Interestingly, there's nothing with a tangential velocity lower than about 150 kiloparsecs around the Milky Way, which matches quite well with what we're seeing when we include the effects of a central galaxy. Okay, so I think I have time to actually read my conclusions. So I want to emphasize that only dark matter-only simulations can provide the statistical samples that we need to really interpret the future observations that we have coming online with things like Gaia and WFIRST. But we know that dark matter-only simulations are just flat wrong, right? They don't include the central galaxy. And that means that they vastly overpredict subhalo counts relative to hydrodynamical simulations, which may be still wrong, but at least they're better. Embedding a galactic potential brings our substructure populations to within 20 to 25% agreement with the full fire simulations, which means that the galaxy alone accounts for about 75% of that substructure depletion. Furthermore, we see that subhalos on radial orbits are preferentially destroyed. Anything that comes close to the center of the galaxy is likely to be destroyed by the galaxy. And as an overall point, we can state that substructure predictions can be much improved relative to dark matter-only predictions at really minimal CPU cost with this embedded potential technique. So in the future, Tyler Kelly, who's sitting back there, one of James Bullock's grad students, is going to be running a statistical sample of Milky Way size and group size zoom-ins with embedded galactic potentials to make predictions for things like substructure lensing and stream heating. Okay, so finally I just want to thank the organizers again, and thank you all for having me.
So since you didn't say it, as far as I know, the data on PAL 5 is that Karlberg and collaborators claimed to have seen the gaps that would have been predicted by these 10 to the 7, 10 to the 8 solar mass subhalos passing through, but Rodrigo Ibata, with better data, does not see them.
Oh, okay. I wasn't aware of that paper, actually.
Yeah.
That's good, because, yeah, that result is actually, the first result that you mentioned is in tension with what we're seeing.
Exactly. Although Karlberg and others claim to see the same thing in other streams, but PAL 5 is particularly good because it's close, and Karlberg had used, I think, Sloan data, and there was a much better image that Ibata used. So, Now, I wanted to ask about the Fiacconi Dow et al. Paper. So they did a more massive galaxy, which would host an elliptical, not a disk.
That's right.
But they did not see this destruction of the subhalos. In fact, they saw an enhancement. So is it the fact that they didn't have a disk, or what other aspect do you think accounts for the difference?
So I talked with Davide earlier this week about it. I'm pretty sure that it's basically an assembly time thing. That our halos, because they're lower mass, assemble earlier, most of the substructure falls in earlier, and therefore there's more time for the subhalos to be destroyed, basically.
So it's really an accretion history story.
That's what I believe.
So different accretion histories could give different results. The reason that's important, these massive galaxies, is that those are the things that are being used for the more distant lensing detection.
Exactly.
For example, by Hezeva. And so it's going to be also important to get those right, and to do these kinds of high-resolution simulations on 10 to the 13 solar mass halos is going to be even more expensive.
Yeah, it's infeasible right now.
Right. So
I'd also argue that we don't have great models for AGM feedback in most of these simulations.
Yes,
so in a lot of ways, these embedded potentials, they let you actually match the galaxy mass that you expect to form.
Yeah, and for the purpose of getting the subhalo story right.
Exactly.
It's certainly a lot cheaper. So if it's believable, it's great. Okay, sorry to have taken so much time, but let's have questions from the audience.
So I'm just curious, so it sounded like in this case you grew your disk potential in the center based on the fire simulation results from the same. So how would you go about deciding how to grow your disk with a different set of initial conditions if you don't have the hydrosim to fall back on, especially in the case where you don't form a disk?
Right. So the idea for this paper is to demonstrate that this method can reproduce hydrosims to pretty good accuracy. The plan for Tyler's paper is to basically use abundance matching and scaling relations from observations to stick in realistic-looking galaxies.
And evolve them.
Exactly. And evolve them in the same way. So while there won't be hydrosims to compare to say, is this right compared to what we see in the hydrosims, we'll, I think, be able to say pretty confidently that it's at least a better prediction than not including that embedded. We have the ability to do that, yeah. We have, I mean, it's actually it's a 3-parameter model. As long as you can describe your potential with 3 parameters, it's straightforward to plug it in. If you want a 4th parameter, I can edit the code in 20 minutes. And
Okay, so 2 questions. I know you showed me a little bit before the talk, but could you comment on the disk's impact on the structure of existing subhalos?
Sure. So like I was saying earlier, I don't see any evidence of strong changes in the structure of surviving subhalos when I include the disk. Now, I think most of those changes are probably coming from internal feedback, which obviously we're not going to capture with this model. And that's then exacerbated by the tidal stripping that the disk provides. But yeah, I'm not seeing anything that really pops out. That said, I haven't looked at it super closely. Like I was saying to you earlier, the mass subhalos that we're looking at are not really too big to fail candidates. It is important for substructure boost studies, and we have someone that's actually working on that to see if we get different answers out, or how different our answers are. But I suspect that that's going to be mostly dominated by just the fact that we have fewer systems in the galactic simulations.
So my second question follows Joe's comment that those galaxies responsible for lensing at high redshift are predominantly elliptical galaxies, and the potentials are larger than the disk galaxies you are simulating. And maybe they don't have so prominent disks, and so the subhalo reduction you see here probably don't exist in those systems.
Right, so there's no disk shocking additionally, you're right. It's strictly tidal stripping and destruction in that case. But we haven't run any of those yet, so I can't really comment on it. It's pure speculation.
Well, also the point you made that the subhalo survival may depend on the history, the formation history, means that you probably have to run a bunch to get some kind of system. And of course we will, assuming the success of the ALMA program for Hezeva and the various other programs, we will in fact have lots of data.
Yeah.
So having a bunch of simulations is probably also going to be essential.
Exactly, yeah, I agree.
Any other comments or questions before we get into the general discussion? These are actually, we're including the discussion in the recordings, and might as well put it.
I just wonder if you care to speculate what the remaining 25% that you don't see of the substructure depletion, I mean, is there any way that you could capture that some other way?
So part of the answer, I think it's my next slide. No, let me skip that. Part of the answer, I think, is that, so this is plotting the mass within the baryonic or actual baryonic mass within 10 kiloparsecs. The dashed lines here are the disk models that we put in, whereas the thin lines are the stars in the fire simulations, which are what I'm matching to. You'll notice that before sort of the redshift 1.5 to redshift 1, a lot of the baryonic mass is in gas, which I'm not including. So I think adding that in is going to get us closer. If we make the potential, so we're using a Miyamoto-Nagai potential, which is relatively soft in the center. If I artificially squash the disk vertically, that also gets us closer. Can show you that in this cyan line here. Or if we just double the mass of the potential, that also gets us closer. So I think as far as the destruction from the central galaxy, it's really driven mostly by the amount of mass that you have within a given radius, and furthermore by how shocking basically the disk is.
Okay. Well, let's thank Shay and all the speakers.